Hi there, this is Ayush from Master Mechanical Design, and today we will understand a very important and very fundamental concept of GD&T, which is material condition. Maximum material condition MMC and least material condition LMC. What does it mean in general, and what does it mean when we apply as a modifier within GD&T control frame, whether with position control or flatness or any other geometric tolerance. We will also discuss when to use MMC modifier and when to use LMC modifier. Additionally, we will also look at why MMC is more commonly used than LMC. And most importantly, why MMC material condition is necessary in most real-world cases. Also, where we should not apply any modifier, where we should actually avoid applying MMC or LMC modifier. So let's start with MMC. So MMC or maximum material condition is the condition in which a feature of size contains maximum amount of material within a specified size limit. For example, let's say we have a shaft with diameter 20 mm and tolerance of plus minus 1 mm. This means this shaft diameter can vary minimum of 19 mm to maximum of 21 mm along its length. Somewhere it might be 90, in some section it might be 20 or 20.5 or 21 mm. Or it could be a constant diameter, let's say 19.5 mm along the entire length of the shaft. So could you tell me at which condition, at which diameter will this shaft contain the maximum material? In another word, when this shaft will have maximum volume, because at maximum volume shaft contain maximum material, MMC of the shaft. So yes, you guessed it right. It will occur when the shaft is manufactured at largest diameter along its entire length, which is 21 mm in this case. So the MMC of this shaft diameter is 21 mm, the largest possible diameter of the shaft along its entire length. Now, let me take another example. Let's say we have a cubic block with a through hole in the middle, where the hole size is 20 mm plus minus 1 mm. Now, in this case, what do you think? When this block will contain maximum material, what will be the MMC of this block? In other words, when this block will have maximum volume. Is it when the hole diameter is at largest size 21 mm or when the hole diameter is at smallest size 19 mm? So if we only focus on overall volume of this block, it becomes clear that when the hole is smaller, the block overall volume is greater, because a smaller volume removes less material from the block compared to the large hole which cut out more volume from the block. Therefore, the block with the smallest hole size, which is 19 mm in this case, will have most material. So the MMC of this hole diameter is 19 mm, the smallest possible hole size in this block. So to summarize, for a shaft which is an external feature of size, MMC is the largest size. And for the hole which is an internal feature of size, MMC is the smallest size. I hope this is so much clear to you, because as a beginner we often think that MMC means largest size and LMC means smallest size. But this is not the case. MMC and LMC do not directly represent the size. It's actually represent the material condition, maximum material conditions and the least material condition. Now, what about LMC? So LMC, least material condition, is opposite of MMC. It is the condition in which a feature of size contains the least amount of material within a specified size limit. For example, for the same shaft, the LMC will be 19 mm because the shaft will have least volume at 19 mm diameter along its entire length. And for the same hole, LMC will be at 21 mm diameter, which is the largest hole size. So for a shaft, which is an external feature of size, LMC is the smallest size, and for the hole, which is an internal feature of size, LMC is the largest size. It's just reverse to the MMC. Now, if you are wondering what a feature of size is, so I would recommend you to watch my previous GD&T video for complete explanation on feature and feature of size, including regular and irregular feature of size. But just in long story short, a feature is anything on a part that can be touched. All the surfaces of a part are features that can be shown in a drawing. But feature of size is more specific and refers to only cylindrical surface, spherical surface, and parallel opposed surfaces. Look, this is important because MMC and LMC only applies to feature of size, not to the feature. Let's understand it with this drawing. So, the block width is 100 mm plus minus 1 mm. Since the width having parallel and opposed surface, so this is a feature of size, an external feature of size. So the MMC of the width would be 101 mm and LMC would be 99 mm. For this length, which is 200 mm with tolerance of plus 0.5 mm and 0 on lower side, this is also a feature of size. So MMC will be 200.5 mm and LMC will be 200 mm. For this slot, which is 10 mm with tolerance minus 0.1 mm and 0 at upper limit, this is also a feature of size, but this is an internal feature of size. So MMC will be 9.9 mm and LMC will be 10 mm. Now consider this hole at 15 plus minus 0.5 mm. Since this hole is cylindrical surface, an internal feature of size, so MMC will be 14.8, 15 minus 0.2, and LMC will be 15.2, 15 plus 0.2. Now what about this radius, which is 5 mm plus minus 0.1 mm? Since this dimension is not a feature of size, it doesn't have parallel and opposed surface, nor it's a complete cylindrical surface. So we cannot define MMC or LMC for this radius. Similarly, for this center distance 75 mm between this hole A and B, so since this dimension is also not a feature of size, so material conditions like MMC or LMC are not applicable here. I hope you are now clear on what MMC and LMC are and where we can define the size as MMC and LMC. Look, if you are still a bit confusing about what feature and feature of size is, means where we can define MMC or LMC and where we cannot define MMC or LMC condition. So just remember this, that MMC and LMC is only about the size, the actual size of the something which contain a volume, like length or width of something, the diameter of a cylinder. It is not about all the dimensions like locational dimension or radial dimension or anything else. The another question you might have, why do we need to define MMC or LMC of a feature of size? If there is already a defined tolerance, why not just call them upper limit or lower limit of the size? So, well, in my experience, MMC and LMC play a bigger role as a modifier in GD&T control frame, which make them more than just upper or lower size limit indicator. So let's understand the role of MMC and LMC as a modifier in GD&T control frame. So the first thing I would like to say is in GD&T control frame, the MMC and LMC modifier can be applied at two places. One is with geometric tolerance, for example with positional tolerance, with flatness, with perpendicularity, and the second is with size datum feature, like with datum A and datum B. In this drawing, the datum A and B are the size datum feature. In this video, we will only focus on MMC and LMC modifier with geometric tolerance. We will cover the use of modifier with size datum feature, often called datum shift, in future lessons once we fully understood the datums. So there are two places where we see and apply MMC or LMC modifier. Just keep in mind that MMC or LMC modifier do not apply to the size tolerance, dimension or any other location. Applying them anywhere else like this would be meaningless or out of the rule of GD&T. Now, when MMC modifier M in circle or LMC modifier L in circle is applied with geometric tolerance, let's say with position tolerance, in this video we will mainly focus on modifier with position tolerance only, as it's easier to explain and understand for beginner. However, the concept of MMC and LMC is the same across all the geometric tolerance, and we will get into that towards the end of this lesson. So when a MMC or LMC modifier is applied with a geometric tolerance, their meaning change a bit that we have discussed so far. To make this clear, it's actually more accurately to say at MMC or at LMC. The word at is just silent here. I don't know why. So for better understanding, let's first understand this whole thing without any modifier. And then we will understand with MMC modifier and then with LMC modifier. Alright? So when there is a no modifier is applied in GD&T control frame, then there will be no relation between these two tolerances. The position tolerance 0.5 mm and the size tolerance plus minus 1 mm will be treated independently. Means the position deviation is regardless of the size deviation. And this is why this condition is called regardless of feature size, RFS. And as per GD&T rule 2, when no modifier is applied, then regardless of feature size will be applied by default, which we will understand more deeply in next lesson, GD&T rule 2. So in this drawing, the size tolerance plus minus 1 mm controls the allowable variation in pin diameter. For instance, as the diameter is 20 mm with tolerance plus minus 1 mm, so the pin diameter can range in size from 19 mm LMC to 21 mm MMC. And on the other hand, the position tolerance specified how much the center line of this pin can deviate from its nominal position. So this 0.5 mm defines a cylindrical tolerance zone that a pin center line must be within. Something like this. And the position tolerance zone is a fixed, no matter what the pin size is, increasing or decreasing. Means if the pin size is produced at MMC 21 mm, allowable position deviation will be 0.5 mm. If the pin is produced as 20.5 mm, the position deviation will still 0.5 mm. Pin size 20 mm, allowable position deviation 0.5 mm. Pin size 19.5 mm, allowed position deviation 0.5 mm. Pin size at LMC 19 mm, allowable position deviation will remain 0.5 mm. Which seems good and tight, but this creates a significant challenge during inspection, especially with functional gauge, go or no go gauge. For example, if there are 4 pins on this plate, we cannot simply use a fixed go-no-go gauge to check their position because it would not account the size variations. Instead, we need a variable size gauge, one that could first adjust the different pin size, and then we can see where the position of each pin is. So this makes inspection more complicated and expensive because it requires specialized equipment. Basically, a CMM would be needed to ensure that the part meets the positional tolerance across all the possible sizes. Now let's consider a real-world scenario where we are assembling the two parts. Let's say there's a pin that needs to be fit in a hole of this block. And let's say this pin is at largest allowable size 21 mm, which is MMC of this pin. So when the pin is at this size, the fit between pin and the hole is tight. There isn't much room for this pin to move around within the hole. So if it's not positioned exactly right, it wouldn't be fit properly. And because of this tight fit, the pin position must be very accurate. Now let's consider the same pin but at a smaller size, 19 mm, which is LMC of this pin. So at the smaller size, there is a more space around the pin when it is fitted in this hole. And the important thing in which I want you to be interested in is this extra space. Means the pin can be slightly off from its exact position, more than it could be at 21 mm. It's MMC condition. For example, if the position tolerance is originally set at 0.5 mm for the pin diameter at 21 mm, at 19 mm the pin might be able to move up to 2.5 mm off from its position and still fit. So the key idea here is that a smaller pin allows more room for positional deviation. When the pin is at a smaller size, there is a more space around the hole, which means it can shift more and still fit. On the other hand, when the pin is at largest size, there is a less space around it. So it's positioned to be more precise to ensure it's fit correctly. However, when no MMC or LMC modifier are applied, means we are using regardless of feature size condition, the position tolerance remains fixed no matter the size of pin. This means even if the pin is smaller and there is extra space that could allow it to fit despite being slightly off, but it would still be subjected to the same tight position tolerance as if it was at its maximum size 21 mm. This causes a problem where part failing inspection because its position isn't within the tight tolerance, even though the part would work perfectly in actual assembly. In other words, a part that is functionally okay could be rejected just because it doesn't meet a position tolerance that was set for the different size condition. What I mean to say is the position tolerance 0.5 mm might be set for the pin where it's a 21 mm at MMC, where the tightest control is needed due to snug fit. But when the pin is smaller, like at 19 mm, this tight position tolerance isn't necessary anymore, since there is a more space for the pin to adjust within the hole. Therefore, it makes more sense to allow the pin more positional deviation at a smaller size. This is exactly the MMC modifier allows, providing bonus tolerance as the feature of size deviate from MMC to LMC. By using the MMC modifier with geometric tolerance, we accumulate these practical assembly conditions, allowing parts more positional flexibility as it gets smaller. And this ensures that parts that are still functional pass the inspection. So applying the MMC modifier with positional tolerance, let's say with 0.5 mm in this example, we are communicating that position tolerance 0.5 mm only need to be exact when the feature of size is at maximum material condition at MMC. This means when the pin size is at maximum of 21 mm. If our feature of size, like our pin, gets smaller, the allowable position deviation will be increased by the same amount the feature of size decrease from MMC to LMC. And this extra deviation is known as bonus tolerance. To put it mathematically, bonus tolerance equal to MMC minus actual size. So the total position deviation allowed for the pin will be position tolerance as MMC plus bonus tolerance. So in our case, position deviation equal to 0.5 mm plus bonus tolerance. So when the pin size is at MMC 21 mm, bonus tolerance will be 21 mm minus 21 mm. MMC and actual size is same, so it will be 0. Total position deviation 0.5 mm. If the pin is produced at 20.5 mm, bonus tolerance will be 21 mm minus 20.5 mm, 0.5 mm. So the total positional deviation will be 0.5 plus 0.51 mm. If the pin is at 20 mm, bonus tolerance will be 21 minus 20, 1 mm. Total position deviation 0.5 mm plus 1 mm, 1.5 mm. If the pin is 19.5 mm, bonus tolerance will be 1.5 mm and total positional deviation will be 2 mm. If the pin is at 19 mm, the bonus tolerance will be 2 mm and the total position deviation will be 2.5 mm. I hope this is so much clear to you. In this video, we have understood the concept of MMC with a pin or a shaft, which is an external feature of size. But the same principle also applies to internal feature of size, like a hole. When we apply MMC condition to a hole, which is an internal feature of size, the concept works similarly. At the MMC of the hole is at a smallest size in this condition. The position of the hole must be more precise because it has less space around the hole for the position variation. But as the hole size increases, moving from MMC to the LMC, remember the LMC of the hole is largest hole size. The allowable position deviation increases because there is a more space around the hole for deviation without affecting the assembly fit. For instance, let's say this is a motor mounting plate with a central hole for motor positioning, which is a slide fit, and 4 clearance hole for mounting bolts. Here, the central hole position is crucial for aligning the motor, so it would not use MMC modifier. However, the 4 mounting holes are mainly for fixing the motor to the plate and do not have critical positioning function. So by applying the MMC to the positional tolerance of these mounting holes, we allow them to have more positional freedom as the hole size increases. If the hole size are produced slightly larger than the minimum size, they can be a bit off position while still fitting correctly with the bolts. And this is where the MMC modifier becomes useful in assembly. It provides flexibility by allowing the part to have more positional variation while still meeting the functional requirement. Additionally, the inspection process is simplified with MMC modifier because we only need to verify the virtual condition. For example, if there are 4 pins on this plate and the pin diameter is 20 mm plus minus 1 mm with position tolerance 0.5 mm, the virtual condition of each pin will be 20 mm diameter at MMC plus maximum positional deviation 0.5 mm, 21.5 mm. So if a functional gauge or fixed go gauge with 4 holes of 21.5 mm at nominal distance pass through these holes, this part will be acceptable. We wouldn't need an adjustable gauge or CMM to inspect. If you are wondering what is virtual condition, so we will dive deeper into virtual conditions and worst boundary condition in the upcoming lesson. Now, in some situations, we must avoid the MMC to be not used. Let's understand it with an example. Let's say we have a high-speed drive shaft and having multiple steps. These end steps are designed for the bearings and coupling, and the middle portion is just to maintaining the distance. So the middle portion of the shaft need to be controlled with respect to the end step to maintain the balance. So their position should be accurate with respect to the end steps. Now, if we are applying an MMC modifier to the position of this middle section, it could lead to a problem. Here is why. If the shaft diameter is not at MMC, the middle portion could deviate more from its ideal position because of the bonus tolerance. And this deviation will cause the shaft to become off-center, which cause an unbalanced mass. And in a high-speed rotating shaft, this imbalance can lead to excessive vibration, which will be highly undesirable. So in this case, applying MMC modifier would be a mistake. Let's take another example. Let's say we have a two-step shaft, where first step is need to be press fit and the top step needs to be slide fit in this block. So in this situation, the press fit step must be accurately positioned relative to the top step. Now, if we apply a MMC modifier to the position of this step, and if the step isn't at maximum material size, the step can be deviate from its center because of the bonus tolerance. And this deviation could be cause uneven contact with a large interference at one side and might be clearance on the other side. So the rendering of the press fit will not be effective. So MMC modifier should not be used here either. So this was all about the MMC modifier with the position tolerance. Now MMC condition can be also applied with the other geometrical tolerance like flatness, straightness, perpendicularity. For example, let's say this part flatness is defined at MMC condition. Means when a part thickness is at MMC, the flatness is tighter. The flatness tolerance is tighter, and as the size of this part thickness goes towards LMC, the allowable flatness deviation can be increased, something like this. Similarly, with the straightness of the shaft, when the shaft is at MMC, the straightness tolerance is limited, and as the shaft size decreases towards LMC, under a specified limit of course, the straightness tolerance can be increased. Same with the perpendicularity. At MMC, the part must be more perpendicular accurately, but as it moves towards LMC, the allowable deviation from perpendicularity can be increased. But as these examples look very simple, straightforward, but this is not. In this all example, the GD&T rule 1 is overwritten by GD&T rule 2, which we will understand in next lesson, otherwise you will miss a very important concept. And this is why these starting lessons are very important if you want to understand GD&T as it is, as GD&T is. It is complex. Now, what about LMC modifier? What if we apply LMC modifier with position control? For example, if we apply LMC, L in circle, with position tolerance 0.5 mm, so it just refers to MMC modifier. It means the 0.5 mm position tolerance applied when shaft is at its LMC size, say 19 mm. And as the shaft size increases towards MMC 21 mm, the allowable position deviation will increase. This means if the shaft is at 19 mm, the position tolerance is 0.5 mm. If the shaft diameter is 20 mm, the position deviation could be 1.5 mm. If the shaft diameter is at 21 mm at MMC, the allowable position deviation would be 2.5 mm. But this doesn't make any sense for most of assembly condition. In assemblies, if the part size is towards MMC, the position deviation should be smaller to ensure the good fit. Otherwise, part wouldn't fit correctly. Therefore, LMC is generally not used for the assembly condition. Instead, we use LMC modifier when we maintain a thin wall thickness, and at the same time we allowing the bonus tolerance. What I mean to say is, let's say we have a nylon block with a hole near its edge, and hole has size tolerance 20 mm plus minus 1 mm, and its position tolerance is 0.5 mm relative to datum A, B and C. This face is datum A. So the wall thickness is very thin, and let's say we need to ensure that it doesn't go below 2 mm. If the hole size increased to its maximum, let's say 21 mm at LMC, even with the maximum position deviation 0.5 mm. So to ensure this, we can specify a basic dimension from datum A, which would be 2 mm, the wall thickness, plus the radius of this hole at LMC, which is 21 divided by 2, 10.5 mm, plus the radius of position tolerance diameter 0.5 mm divided by 2, 0.25, say 12.75 mm. So if the hole size is at 21 mm at LMC, the position tolerance is 0.5 mm and the wall thickness is maintained at 2 mm. If the hole size decreased to 20.5 mm, moving towards MMC, the position tolerance remains 0.5 mm but wall thickness now increased to 2.25 mm. If the hole size becomes 20 mm, the position tolerance will be still 0.5 mm and the wall thickness further increased to 2.5 mm. However, the goal is only ensure that wall thickness does not fall below 2 mm, and this is where the LMC modifiers comes in handy. By applying the LMC modifier indicated by L in circle to the position tolerance, the hole can deviate more from its nominal position as the size decreases towards the MMC. For example, if the hole is 21 mm at LMC, the position deviation allowance is 0.5 mm, maintaining 2 mm wall thickness. If the hole size reduced to 20 mm, it's moving towards MMC, the bonus tolerance will be LMC minus actual size, 21 minus 20, 1 mm. Meaning the total allowable position deviation becomes 1.5 mm, while still maintaining the 2 mm wall thickness. If the hole size is at smallest size, let's say 19 mm at MMC, the bonus tolerance is maximized to 2.5 mm, but again 2 mm wall thickness is maintained. So using the LMC modifier ensure that even the hole size decrease giving bonus tolerance, but the wall thickness requirement is never compromised, providing the flexibility in manufacturing while preventing the part integrity. So this is it for this video. If you have any doubt or any question, please let me know in comment. The next lesson should be on your screen or you can check the description. Thank you so much for the watching.